protection. The picture in the middle is not the way to do it. Okay. Take the piece of what used to be cigarette pack foil, so any foil, and wrap it around the fuse. Pop it back in.
Gum wrapper.
Gum wrapper, yeah, same thing. Yeah, no, don't do it. The truth is, fuses do occasionally just go. A fuse that's operated at 80 or 90% of its capacity regularly will wear out, will eventually age and eventually go. They can be remarkably difficult to see that they're blown. The really super fine wire ones, it's like. Same thing here. These aren't. Kind of from the side, it's fairly easy to see that it's blown, but from the end, sitting down in a holder, it actually can be very difficult to see that they're blown. Yeah, and the idea of repairing them with your needle nose pliers or your scissors or some other magic fix, scary. So the purpose of this device is to protect the circuit. If your $22,000, wide angle fender bearing gets destroyed, we don't care. It's not there to protect that load. It's there to protect the circuit. If the circuit's designed correctly, the load will fail before the rest of the circuit will. Right? And it'll stop conducting current. It'll fry, it'll short, it'll one way or another stop working. The real goal of circuit protection is if something damages the circuit itself. Now, is it possible for a load to internally somehow fail and overload the rest of the circuit? Yes, it's possible, in which case the fuse would blow or the circuit breaker would blow anyways. And at that point, the load's toast because that's what fried everything in the first place. But at the end of the day, circuit protection is there to protect the wires, any other connectors, components, etc., related to transmitting electricity from the power source, or in this case, from the circuit breaker, hopefully as close to the power power source as possible, all the way out to the load, and then from the load to ground. Okay. So we're okay with the load being damaged and so on. The truth is, most loads, they're encased in some kind of a metal box. The toaster's in a metal box. Your laptop, the part where it's got the power supply, is in a little metal box. The light fixtures, there's a metal box surrounding it. So any place where there's an electrical device that could potentially create fire is usually encased in metal somewhere. Something that will withstand reasonable temperatures. So if it fails, fries, blows smoke, that's all you're going to get is smoke coming out. And any flame that happens is going to put itself out pretty quickly. Conversely, we would then theorize that any circuit must be designed such that its power sources and loads won't exceed the current carrying capacity of the conductors. Right? That's part A. Part B that we have to consider is that the insulation of the entire circuit also won't exceed the voltage specifications of the circuit. Because if I bring the voltage up enough, it'll blow a hole right through the insulation. Well, this we don't consider too often because for the most part, most wire we make it to be good up to like 250 volts or something like Okay, and then even bigger wires, even better. But so when you look at the spec for mil spec wire, etc., the voltage rating on it's usually pretty darn high. So you can use it for 32, 24, 28, 120. It works for all of it. So we tend to disregard that value, but the truth is the rating for the wire needs to both insulation so that the voltage doesn't leak out and current carrying capacity so that it doesn't overheat. Now there are some exceptions. What about high energy ignition systems? Okay, the secondary on an ignition system or a turbine igniter, now you're up in 15, 20, 30,000, 40,000 volts. Really high energy ones, 100,000 volts. You darn well better be paying attention to insulation, because at that kind of voltage, and given that the spark has a choice of going through an air gap in a very high pressure environment, which is hard for electricity to do, or leak through the insulation, it's way more inclined to leak through the insulation. Okay, so we have to pay very close attention to the insulation characteristics. The other characteristic of insulation that generally, while it may be in a mil spec, it's generally not talked about is, and this is where the below occurs, is the mechanical protection quality of the insulation. To prevent chafing, to prevent some mechanical abrasion that causes the insulation to be penetrated, no longer insulate, and then you really, really let stuff out. That one on that side, that wall, that used to be something somewhat like this. Okay, but somehow or another, things went bad in there, and it got pretty nasty. The other one is just a pretty classic example of probably an extension cord that got dinged. Have any of you ever taken the skill saw and cut right through the cord, or the weed whacker, or the hedge trimmer, or the none of you are raising your hands. Okay. I think you're all liars. We've all done something stupid like that, but okay. So typically, voltage rating, it's there. If we've adhered to mil spec, which means essentially we buy it from a reasonably well-known vendor, Chief Aircraft Screws, or for buying it in bulk at a manufacturing level, we are ordering it from a wire company, reputable wire company that's building it to a mil spec, and we're going to get with the wire we buy an 8130 tag that indicates the authenticity of the wire, where it came from, etc. All right, so yeah, the mechanical protection and thermal characteristics as well. Again, it's very unusual for us to run a wire in an environment that's much higher than 300 degrees. And in truth, even most engine compartments, even though the cylinder heads are at 350 degrees, etc., where the wires tend to go, it's a whole lot cooler. It might be 150, 160 degrees with all the air that's going through. So it's way, way within the parameters for your standard mil spec Tefsel wiring. Really no problem there. Not so with PVC insulation, but PVC is also very obvious. It's got this sort of flat, completely, there's no translucency to it at all. It's sort of funky, flat, completely opaque color and texture that looks very much like a PVC pipe, although it might be a blue, pink, or something like that. So, as we remember from DC, material choice, which is also kind of moot for us, because it's going to be copper, right? Might be some slight derivations of copper, like we might add a little tin or zinc and call it bronze or brass, but ultimately it's going to be copper. There's a few exceptions, like Piper Cherokee 140s, where they put the battery in the back, and rather than having this 10.5-foot copper cable, they went with aluminum, which creates such a huge voltage drop that it would go through starters left and right. There are some cases where other metal is used, but it's pretty rare. It's pretty much copper. So as far as we're concerned, the two parameters that matter to us the most are cross-sectional area, or wire size, for the American wire gauge system, or, and the other parameter is the length, right? And so we use charts which are based upon a certain amount of voltage drop. The truth is, within the wire gauge system, you, in fact, you go online, there are calculators, but they have a chart that shows voltage drop for any wire using standard copper wiring, multi-stranded wiring. There's a little bit more voltage drop with multi-stranded wiring than single solid core. However, solid core isn't flexible enough for use in an airplane. Okay, so now the other thing is any conductor does provide some resistance and therefore some heat. So we can use that to our advantage when it comes to circuit protection. We can make a weak link, which is what a fuse is. We actually could put in a circuit a section of wire that's designed to create a voltage drop. For many, many, many years before we went to electronic ignition, all automobiles manufactured, pretty much universally across the board, the ignition circuit, the points and the coil ran at 9 volts. 9 volts, you say? I'm old enough. I had one of them cars that ran at 12 volts.
6 volt.
Well, you might have had a 6 volt, but they never kicked them up above 9 volts. What they did is they put a short little section of wire in the wiring harness that goes out to the coil, right out to the points of the coil, and it creates a certain amount of resistance. It's also a weak link. They called it a fusible link. Okay? And I more than once have seen individuals, for whatever reason, the fusible link fails. Age, whatever. They don't realize it was a fusible link, so they just fix it. Put a piece of wire back in there, and everybody's good to go. Only now the coil points and condenser are all running at 12 volts. So it starts going through, it usually goes through points very quickly. And then, of course, they don't tell you that they fixed the little wire there. Right? Took out the fusible link that was designed to be there. We can also use that to be the element that causes the circuit breaker to blow. Or we could use it to be the element that actually does physically go poof inside the fuse. Right? So anytime we're talking about heat, we really have two equations we have to deal with. The first is how much heat will it generate. The second is how much heat can it reject over time. Right? If it can reject all the heat it can collect, then it'll never get hot. However, if we insulate it with a bunch of other wires, then it's not going to be able to reject heat nearly as quickly. So it'll tend to run warmer. So that's why those different charts for in a bundle, into conduit, single free air, and then of course limited duty versus continuous duty. So basically, if I've got one circuit that I'm going to have circuit protection on, I got that circuit breaker there. I'm going to add up all the users on that circuit breaker and make sure they don't exceed the total output for that circuit breaker. Now, it may well be I don't necessarily want a bunch of stuff on the same circuit breaker. I mean, I really wouldn't want my nav lights and my fuel pump on the same circuit breaker. It just doesn't logically make a lot of sense. There are some cases where you see stuff like that. It's predominantly in something like that barely has an electrical system. Okay, it's an old air coupe. It's got a strobe light, a battery, a voltage regulator, starter. I'm running out of stuff.
They didn't have lights.
Probably not. Might. Okay? In that instance, I might truly only have 2 circuit breakers in there. Okay? One for the starter charging and the other for, I might not have much more in there. But because the system is so rudimentary, and that and the plane really flies very nicely without any electrical system at all. I may have a tap coming off with an inline fuse for my handheld radio. Okay, yeah. Of course, I'm really going to go fancy. Coming off that tap, I'll also have a lead running over to the battery for my GoPro, because got to have a GoPro in an air coupe. All right. So we figure out how long the wire is going to be, what it's got to be, voltage drop, which usually is something less than 5%. It's really usually right around 2%, something like that. So we don't want to see too much of a voltage drop. And that voltage drop is going to be dependent on not only length of the wire cross-sectional area, but also the amount of current going through, right? If I increase the current, doesn't the voltage drop increase? Okay, so I'm going to need to kind of include all those in there. They are integrated into those charts already in 4313. Then I can figure out what wiring to use. The circuit protection device is really, it's the amperage. The choice of circuit breaker or fuse, kind of up to you. They both have their pros and cons. In the case of a fuse, particularly a fast blow fuse, you can get a fast blow fuse to react very, very quickly. I can make a digital circuit sensing that will trip quicker, but it'll be a pretty darn expensive thing. The standard typical circuit breaker works off of an element getting hot, getting heated up to the point that it eventually trips. And they're pretty casual. A fuse, normal fuse or even slow blow fuse, you'll see in that chart the amount of time it takes to trip. If I'm at 100%, it's not going to trip. At 125, it may not trip. At 150, it's going to take about 500 seconds to go. Somewhere sort of above that, it's like dropping off. I can be at 300% the fuse capacity, and it'll still go for a whole second before it blows. That's going to be a pretty slow acting device. They make them where they're way, way quicker. The top end of that chart is that 500, that might be 500 milliseconds or half a second. And all the way down in there, you're getting into the millionth of a second. So we've got some really, really high speed ones. Where that's needed. In most cases, the downside of a high speed acting device is any very short-term transient that gets through is enough to trip it. That is enough to blow it, right? And in most circuits, a short-term transient of current or voltage, when I say short-term, 10 or 20 or 30 milliseconds, it's not ever going to be long enough to cause the circuit to get warm. This isn't long enough. It takes a while for them wires to heat up. Unless it's serious, you know, it's a lightning bolt or whatever. And if it's really, really serious in terms of voltage and current, your circuit protection may not matter. It may be able to just blow right through it. Okay, so this kind of describes, in fact, every fuse, if you know, like you're buying it from Digitech or one of the other ones, they have the spec sheets on them that tell you all of this. Okay. typically, if I've got a really dirty circuit, I'm going to want somewhat of a loose circuit protection, a very slow activating circuit protection. And unless I've got something that I really don't want to get broken, in which case the better thing to do is to clean up the circuit and put in circuit protection within the thing that cleans up the circuit. Like backup power supplies for computer systems. They're way more than just a backup battery. They're doing, in fact, they're using the battery to filter a whole bunch of stuff. They're doing all kinds of things to condition so that the computer gets really, really clean current coming in, and it provides a circuit protection. So again, as I said, transient current flow, circuit protection takes a while. Now, if it's AC, these little transients, they actually almost instantaneously show up as a blip in the frequency. And that's why major power systems feeding power all across San Diego and the country, they pay more attention to what the frequency is doing, because that'll be instantaneous and they can feel it instantly. So if there's a blip, like a big massive short, that's going to create a frequency, we call it an echo for lack of a better description, that all the relays, main power relays, in proximity to that thing will go, whoops, we got a frequency blip. That could be a short, and we sense that at the speed of light. Trip out. We'll default to breaking the circuit, put everybody in the dark, but that prevents us from blowing a bunch of stuff up. Okay? That's what happened back there in about 2012. Okay. So in an airplane, we don't want the fire to come out of the wire. We really don't want smoke coming out of the box either, but in most cases, the metal box will contain any fire inside there. There's nothing to contain the fire inside the wire. And once the insulation melts, there's really only one way to stop the fire. Turn the master switch off and pull out a fire extinguisher. Because if it's engaged, even with the Tesla wiring, etc., it will self-suppress over time, but it'll take a little while. Meanwhile, whatever's burning is producing all kinds of toxic nastiness that you may have no choice but to breathe. Okay, so truly, and like I talked about the standards with the network or USB or some of these other things, if it needs protection, it should be designed to have it. The load should be designed to have it. And it very well may need protection both on power and on ground and on all the inputs and on the output. So, for example, let's say I've got a device that turns on a relay. Click, boom, relay's on. Big coil in the relay goes, boom, activates the switch. Whatever it is on, the fuel pump or the landing light or whatever, it's on. My device then says, let's shut off the relay. So it does, shuts off the relay. Only all that big magnetic field around the coil says, and it works just like the secondary trying to fire a spark plug in an ignition system. Goes, boom, collapses. Tries to drive a spark back into the switch that just shut off. Use the NPN transistor. If I'm smart, I will have taken a Zener diode and plugged it into the output lead in a forward biased way, so that when that spike occurs, let's say it's a 12-volt system, when that spike occurs, anything above, say, 25 volts, I'll set the forward bias threshold for the Zener diode at 25 volts. Anything above 25 volts just gets shot straight to ground. So that would be an example of output protection. Okay? Particularly in those cases where I know it's going to occur. Anytime I turn that big old inductor off, I know it's going to occur. I've noticed some fuses in here. Also some filtering that will also act as conditioner. Another fuse in here. Okay, I've got several inductors and then your transformer. These guys right here are cleaning things up. That's circuit protection. Transformer intends to clean some stuff up. More filtering. Then we're going to go into, and all that whole circuit is, it's just a power supply. Looks like a computer power supply. 5 volt and 3.3 volt. But all of that's done to condition and make a nice clean DC current coming out with a fair amount of circuit protection. That actually could be the biscuit you've got that you plug your laptop in. I don't remember where I got it. You know, it's also important for the power supply to be appropriately rated. If I try to start an engine, a big old engine on a 2 amp hour battery, what's going to happen? Battery doesn't have a lot of capacity. So I'm going to go, wah, 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 and I'm going to turn it off. Now I get this big, huge magnetic field around the starter. It's going to go kablam and try to go back into the 2.5 amp hour battery, which doesn't have near enough capacity to handle that. So it might go somewhere else. Simply because it didn't have the big battery, the appropriate rated battery in there. So it's important to note that in many cases, the DC battery that you have sitting in there works just like a capacitor. It helps to absorb garbage, particularly high energy garbage, like that might come off of a starter or another relay closing. Similarly, the generator needs to be appropriately rated, and the generator and the battery need to be appropriately rated in combination, both in voltage and capacity. One of the things that's going to happen, if I take my starter, oh dang, I left the mixture out. Okay, now my battery is, got some hurt on it. I've thrown 25–30% out. Field regulator on it, everything on it. Boom! Okay, I got a 900 amp generator in there. Okay, the engine's running 900 amps. And the battery wants some juice now, right? It's going to try and eat that 900 amps. Probably not good for it. But if the generator would give it, it would try to eat it. So you really want a generator that's, and both of the power supplies reasonably well balanced. Now, you and I aren't going to be changing those in normal service requirements, but so the other thing is, somewhere or another, we kind of need to know what the battery is doing in terms of current, or the generator is doing in terms of current. We need to have one or the other. Okay, so we're going to have some kind of an amp system in here. They came up with 2 ways of doing it. They came up with different names for them. So we can take our amp gauge. Now our amp gauge is typically going to be, I'm going to just have a resistor in here, right? That's going to create a small voltage drop. It might be like a 0.0025 ohm resistor. I'm then going to measure the voltage drop across there with my little meter. And that's going to tell me, I'm going to change the label and make it so it shows me amps. Okay, you guys did all that. In fact, I think you guys wired up the Simpsons so that it was an amp meter, didn't you? Isn't that one of the DC practices that you did? Okay, so we're going to do the same thing. If we take that shunt, that little resistor, actually a big old fat thing, and put it between the battery and the bus, we're going to call it one thing. If we put it between the generator and the bus, we're going to call it something else. Okay, so we can take our bus right here and we can say this is battery, and up here we can say this is DC generator. Okay, and then we can either have the shunt here, the wires going like that, or the shunt there. Now the only distinction is, in the generator, electricity is only going to go the one direction. And in the battery, it can go to discharge the battery or charge the battery. It can go either way. So in this case, the gauge is going to have to operate a little differently, right? Okay, so if it's between the battery and the bus, we're going to call it an amp meter. I didn't invent this, guys. We're going to call it an amp meter. It's the same exact thing. The only thing that's different is the little data plate. The needle is centered, sprung to the center rather than sprung to the side, and the little numbers plate has got a positive and a negative to it. But the way it works, the shunt, everything else is the same. Okay, so it'll have a plus or minus. Minus for battery, and this is sort of a little weird, minus for battery being charged, and plus for battery being discharged. Because we've got that scenario where I went blah, 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 and it starts, then I'm, it's air ambulance. I've got the heart that I got to transport across the country. Got to get this airplane started. Man, it's, the child's life is at stake. Whatever scenario. Boom, get it started, turn everything on and go. Okay. Now I've got a battery or a charging system, a generator, that's being tasked to put everything is on, plus it's got to charge up the battery. So everything turned on can't exceed some value. Now that could be different depending on the different airplanes. However, the FAA somewhat theorized, yeah, I may overload it a little bit for a short period of time, but the battery is probably going to come up pretty quickly. Okay. By just, starting, it's going to come up pretty quickly. So they came up with a number, round number, 80%. What I would argue is this is one of several reasons why taking off with a significantly depleted battery is taking off with an unairworthy airplane. In truth, if you've just depleted the starter or started the battery 10 or 20% through starting, by the time you taxi out, warm up, do all the rest of the stuff, you're going to have mostly charged that back. Because remember, as long as your RPM moves up just a little bit, that generator is going to be hitting it with 40 or 50 amps. They're going to charge that battery up pretty quickly. If it's stone cold dead or pretty dead, way, way, way down there, you're now taking off with one of your power supplies empty. That's like taking off with one of your fuel tanks empty. Just doesn't make sense. The FAA said 80%. So if I've got all the little whistles and bells in there, and I'm at 79.9%, and I want to put one more light bulb in there, the only thing I can do is take something out or put a bigger generator, bigger wires, bigger everything else, right? Okay. Now, truthfully, if I was at 79.9%, I would have not installed something, around 65 or somewhere. I wouldn't push it that far. Okay, so this is going to show charge, discharge, plus or minus. If I install it between the generator and the bus, I then call it a load meter. I guess for the load on the generator. At this point, the generator hopefully never goes backwards. If it does, it's bad. So we're going to just read from 0 in the positive. In that case, all the system users, except for the starter, that's a different gig, cannot exceed 100% of the maximum continuous duty output. Okay, so if I was in that scenario, 79.9%, I wanted to put another whiz bang in there, I could put a load meter in there, take the amp meter out. I might have to do major alterations putting the load meter in there, but I could do that. It turns out, look what I've drawn here. That's a bunch of parallel circuits. Right? I can just go like this to there, and then this guy, I can just go like that, and have a switch. Use the same meter for both. Now, I don't know that I would do that with an amp meter, just a standard Aviation bulb, but for an electronic flight information system, both my airplanes have a simple thing, I have a little switch. That allows me to read both load meter, what is the generator actually doing, but then I can also flip down and see whether or not the battery is charging or discharging. Now, I prefer being in load meter mode, because in load meter mode, I know when I turn everything on, and the one airplane is 28 amps and the other airplane is about 14 amps. So if something else is going wrong, I'll know immediately that I've left normal deviation, deviated from normal output. Whereas with the discharge and charge of the battery, that'll be gradual. That'll take 10 or 15 minutes. Remember, if the generator stopped working, I had the battery up above its normal voltage, its surface charge. So it'll take a while for that to start coming down. And then I realize, oh, wait a minute, battery's declining, something's wrong. By doing this, that's real handy. I can do that because I'm experimental. But for me, it was like, okay, the shunt is a little thing like that. I can bolt another one of those in. I got to run the wire anyways. And actually, the way I did it most in these was literally from this shunt, hopped over to here, and then over to the bus. But it doesn't care. All right, let's quit here.